Thanks for joining us today as we showcase PlantPredict version 12, and we do a webinar on advanced 3D energy modeling for gigawatt scale PV. All right, so as we mentioned in our webinar description, today we're excited to be showcasing version 12 of PlantPredict, which is our biggest performance leap in years, and it's all centered around our brand new 3D engine. That will be the focus today. We'll start off with a bit of PlantPredict history to set the stage on how we got here. Then we'll highlight the new features of V12 before giving you a quick demo of the new 3D workflow. Next, we'll go into a technical deep dive about the methods and decisions behind our 3D approach and how it compares to legacy desktop software. Finally, we'll close it out with a Q&A. So if you have any questions during the webinar, feel free to submit those and we'll take a look at the very end. So for those of you who may be new to Terabase, we have multiple product lines, but our overall mission is to reduce the costs and accelerate the deployment of solar through software and automation. First, on the left, we have PlantPredict, which is our solar modeling engine. In the middle, we have our construction management software and our automation platform called TerraFab, which has installed an industry-leading 100 megawatts to date and is set to install hundreds more in 2026. As we release the next gen iteration of that hardware. And on the right side, we have our SCADA, plant controls, and performance offerings. Moving on to today's presenters. First, we have Jason Spokes, who is the Senior Product Director of PlantPredict, and he'll be highlighting some of the new features in version 12, plus doing a demo of the 3D workflow. Next, we'll have Arthur Ono, Principal Performance Engineer for PlantPredict, who will be doing our technical deep dive into 3D calculations and explaining some of the computing we're doing behind the scenes to run the 3D analysis. So with that, let's kick it off with Jason Spokes.
All right, thanks for fall. Hi, everyone. Thanks for joining. Really excited to be presenting today. Version 12 is a significant milestone for PlantPredict, and we've got a lot to cover, so let's jump into it. Start with sort of an overview of the PlantPredict suite of products as they are bundled and licensed. And so let's start with our core product on the left. PlantPredict is a cloud-based modern energy model built specifically for modeling utility scale solar and hybrid plants with a long track record and continuous benchmarking against operating assets over a gigawatt. In the middle, we have our Pro and Enterprise products. We call these products our Pro tools, which utilize PlantPredict as the energy modeling backbone. You can use them to perform sophisticated studies easily and quickly from within your browser. Design Pro generates a detailed layout, BOQ, cost estimate, and financial model and supports batch running of scenarios to find the optimal design configuration from an economic perspective. Voltage Pro is designed to enable a simulation-based string length maximization, and Terrain Pro drastically simplifies the process of generating an earthwork assessment for your project site and is specifically designed to assist in the evaluation of terrain following trackers. On the right-hand side of this slide, we have our extensions, which can be added onto Pro and Enterprise licenses. First is our CAD-ready extension, which allows you to integrate Terrain Pro into your CAD-based workflows. We also offer API access to our energy model and earthwork assessment model for custom applications development and batch processing. And finally, we've recently added a third-party application for module soiling, physical modeling, and cleaning economic optimization built by PV Radar and available for discounted pricing when bundled with PlantPredict. Okay, I'm gonna go ahead and turn my camera off. And I wanted to provide some sort of context of PlantPredict from a historical perspective. And this slide provides some key milestones in the history of PlantPredict, which stretches all the way back to 2007. First Solar acquired the software that would eventually become PlantPredict in 2010 and spent several years re-architecting it for the cloud. First Solar envisioned a performance model that could be used during all phases of the project, from development through construction and into operations. This vision has resonated with Terabase, who acquired PlantPredict in 2021 and have continued to steward it forward since. Terabase coupled PlantPredict with legacy SunPower software, which really formed the foundation of our Pro Tools. And with our most recent release of version 12 2 weeks ago, we've taken a giant leap forward in 3D modeling speed and accuracy. So what are the real defining characteristics of PlantPredict if we were to list them? So first, PlantPredict is built on the cloud, built for the cloud. That offers it to be relatively fast, collaborative, and it can also be accessible from a number of different perspectives. So you can access it programmatically through an API, or you can access it through your browser user interface, accessing the same predictions through different approaches. It also means you have no software to install, and it frees up your PC resources when you're running complex computations. It's native sub-hourly, sub-year, multi-year. This means that any time interval or any weather file duration can be handled within PlantPredict with no problem. We support 2 distinct workflows. You can build by block, which is essentially building by spec, sort of a PV-Syst workflow, or you can build on a map, which is a more visually designed sort of workflow. It's tailored for utility scale, ground mount PV, and battery energy storage projects. We have extensive third-party integrations and compatibilities, some of which we'll be talking about today. We have a large module inverter and weather libraries. This includes global libraries, as well as your own company private libraries or resources. We have a relatively complete set of 3D features, and that's really today's focus of the webinar. And I do want to talk for just a second. One of the advantages of PlantPredict is how we treat versioning. So major versions, version 11, version 12, et cetera, have locked prediction logic. And so this means if you run a version 12 prediction today, you can rest assured that you'll get the same result if you run it again a year from now. To verify that, we run several hundred automated predictions prior to each release to ensure results have not changed. We typically release minor updates every 3 weeks or so. And as of 2 weeks ago, version 12, which was previously in a beta stage, has replaced version 11 as the default logic version. All right, so what is new in version 12? Well, first of all, we have completely redesigned or introduced a new 3D workflow and a complete set of 3D calculations. I'm going to be going into more detail on the next slide as to what that entails. We've released a wind-stow model, and to support this, our weather data now supports wind gust data. We have 2 models to choose from, PlantPredict or Array Technologies model through an Array Technologies API. We've improved our AC collection circuit loss modeling. So we've replaced a fixed percentage approach with an I²R loss model. This now is similar to how we treat DC circuit losses or transformer winding losses. We now support sub-hourly battery energy storage predictions, several map builder enhancements, including the ability to export PVC files and the ability to create 3D shade objects, several weather data integration upgrades, and numerous bug fixes. Okay, so let's dive deeper into what is included in the 3D calculations and workflow within version 12. So first of all, we support a site level 3D scene that can be defined via PVC or SHD file upload, 3D shade and shade electrical effect calculations, 3D transposition, plane of array. So this is the plane of array irradiance for all of the different orientations within a 3D scene. Arthur's going to be talking in much greater detail about these last 2 points. A 3D shade factor table export, we're providing this for direct comparison with PV-Sys 10 by 20 shade factor table, if you're familiar with that, and Arthur's going to be also talking more about this. We have several shade electrical effect models, including a new step fractional model. Again, Arthur will be going into much greater detail on that. A new terrain-aware backtracking model. We support non-uniform tracker rotation schedules. So this means you can upload your own rotation schedule for each time step for each tracker. We support 3D shade object modeling. So think trees, wind turbines, things of that nature. We allow you to visualize shadows through the 3D viewer. We support heat map visualizations of the 3D calculation results. We have optional sun position binning. This helps to expedite the shade calculations. And Arthur's going to be talking more about what that means. Additionally, optionally, you can simplify shade objects. Again, this helps to expedite shade calculations, and Arthur's going to explain what that really means. All 3D features are API accessible, and we can support very large scenes. So easily 1 gigawatt plus of terrain following tracker scenes. And the way that we really limit the size of the scene is a 2 billion object, PV collector object times time step limit. So for example, if you have an 8760 weather file, that means that you can support approximately 200, I think it's around 230,000 PV collector objects within that scene. So keep that in mind as a limitation. And last but not least, we're very fast. So for a representative 150 megawatt terrain following project on a complex terrain, we are on the order of 250 times faster than PV-Sys. And Arthur's going to be talking more about some of the direct speed comparisons between the two tools. Okay, so that's a long list for sure, but we've worked hard to ensure the 3D workflow is intuitive and responsive, and I'll attempt to demonstrate that in the demo shortly. Before we get into the demo, I do want to take one slide to talk about the 3D workflow. You'll need to first define your 3D geometry within a PVC file, and there are several Terra-based applications, including PlantPredict, Map Builder, Design Pro, Terrain Pro, as well as third-party applications such as PV Farm, PV Case, which you can export PVC files. PlantPredict is compatible with PV Colada version 1.4 file format, and we're currently reviewing the latest version 2 format from the PV Colada working group. We've also released the ability to alternatively import 3D geometry via SHD file format, although this is still in a beta release stage. SHD is a proprietary PV-Sys format and will enable the direct export of 3D scenes from PV-Sys into PlantPredict. Once the 3D geometry has been imported, you'll need to configure relevant 3D settings and run the 3D calculations. This can all be done from a single page within PlantPredict and with a single button click. Once the 3D calculations are complete, the results are automatically available for the prediction. All you need to do is run the prediction as normal. All right, and with that, I think that brings us to our first poll question. So what tool are you currently using to perform 3D energy modeling? So it looks like the poll is live. I'll give that a minute or two to get in Zoom. All right, so it looks like about half of respondents, a looks like about half of respondents are, it's showing my screen is paused. Okay, I'll just read it out. It looks like about half of the respondents are using PV-Syst, 7% solar farmer, 18% their internal tools, and 23% as other. So I'll close the poll. Okay, and with that, let's step into the demo portion of the webinar. So I'll stop sharing. And now I will share my screen again. Okay, so everyone should hopefully be seeing my PlantPredict's screen. And what I've done is I've created a project, V12 stable release webinar, and I've created 2 predictions within this project, a 2D standard backtracking and a 3D standard backtracking. And these are both the same designs, both the same settings within the prediction. The only difference is with the 3D standard backtracking prediction, I've gone ahead and I've loaded the 3D scene, and I've run the 3D calculations, and the prediction therefore has the basically those 3D calculations built into it. I've already run all of the predictions, and so if we were to compare directly, let me expand this. If we were to compare the energy results from both, we can see that in the simple 2D world, we're at 177.9 gigawatt hours. And in the 3D world, we're at 169.6 gigawatt hours. So that represents about a roughly 4% reduction in total annual energy yield going from a 2D world to a 3D world, just for context. What I'm going to do in the demo is we're going to clone this 2D standard backtracking prediction. So I'm going to go ahead and do that now. And we're going to set up this 2D standard backtracking prediction. We're going to load the 3D scene into it, and we're going to configure it for a terrain-aware backtracking model. And then we're going to run it and run the calculations. You'll see how that happens, and then we will compare the results between the standard backtracking 3D and the terrain-aware backtracking 3D. I think you'll find that interesting. So right now it is cloning. It's going through the process of cloning and copying all of the libraries and information from the 2D prediction into this new prediction. So that takes a minute. It's taking more than a minute. Okay, there we go. All right, so at this point, so this is my clone. I'm going to rename it as 3D terrain aware backtracking. I'll update name. Okay, so for those of you who are not familiar with PlantPredict or the prediction, this is our main prediction page, and it's where we can define our weather data, which has already been defined. So I'm not going to go through that. It's also where we can define the design itself and where we can load our 3D data and set up our 3D calculations. If we wanted to, we could add an energy storage system. We could add interconnection information and design information. And we can also modify some of the model choices for the prediction. This is also where we can run the prediction, and eventually we can go beyond this page and get to the results. Let's take a quick look at the design. In this case, I've set up the design in our map builder environment, which allows me to design in a map interface. Now, alternatively, there is a different workflow to design sort of by spec. In this case, I'm just for visualization purposes, I'm designing in the map. And what I've done is I've gone ahead, this is a 83 megawatt DC project, 70 megawatt AC in Central Texas. And what I've done is I've gone ahead and already defined a couple of 3D objects. So first, I've got this sort of north-south line, which I've given a 30-meter height to represent a tree line. I've got a transmission line running sort of east-west, and I've defined some poles, some towers within that transmission line. And then I've also created, just for fun, sort of a silo in this area to be able to just provide some additional shading. So what I need to do in order to bring this into our 3D environment is I'll first download the PVC file. I'll export that. And then we'll step out of this. When I create that PVC file, what's essentially happening is we're taking this 2D design, and you'll notice that there is 3D data underneath that 2D design. So that's publicly available terrain data, and PlantPredict is essentially going to lay this design over that, within that, the sort of 3D topo data. Now, there are much more sophisticated workflows to incorporate your 3D data or do terrain analysis and things like that. For this demo, we're keeping it quite simple. So let me step out of this. We'll go to our 3D scene. At this point, the 3D scene is blank. I'll upload the PVC file that I just downloaded. And we're presented with our new 3D settings, or our new 3D scene page. Now I can step into the 3D scene and actually view it here. I'm going to hold off for doing that right now, but we'll get to that in a second. I have some information about my 3D scene, and including the total collector area relative to the DC field area. I also have a total PV collector count and a non-PV object count. And I can see that this is set up as a single axis tracker as defined in the PVC file. Within my orientations, this is where I can define what controls the tracker rotation logic. And by default, it's set up to a representative DC field, which is looking for a target DC field to say, I'm going to use that target DC field to sort of drive the rotation logic. And this particular DC field, it's set up as a backtracking model, no irradiance optimization, and no wind stow. This was how we had set up the previous prediction, the 2D standard backtracking prediction. I'm going to change this to terrain aware backtracking. Now, alternatively, this is also where I can define time series schedule and say that I want to be able to upload my own tracker rotation schedule. For this case, I'm going to use terrain aware backtracking. Moving down, this is where we can define the direct shading model. Now, this is a half-cut cell bifacial module in a portrait orientation. So I'm going to select a step fractional electrical shading model with 2 horizontal step fractions per bay. And Arthur's going to provide a lot more context and some visualizations about what that really means. We're going to go ahead and set that up. The binning type is disabled because this is terrain aware backtracking. Binning provides some interpolation between different sun positions to interpolate the shade fraction. We want to disable that for terrain aware backtracking because that interpolation is no longer very accurate. And then lastly, there's a shade object simplification. I'll leave it at the bounding box with fast. Arthur's going to talk about that in a little bit. So at this point, our settings are complete. And over to the right, this is our calculation wizard. I'm going to go ahead and queue these calculations now. And because I've selected a terrain aware backtracking model, our orientations have to be first calculated. So before we calculate transposition or shading, we have to calculate what are those terrain aware backtracking angles throughout the scene. If I had used a representative DC field, the orientations would have already been calculated and loaded ahead of time. So once the orientations are finished calculation, then the wizard moves on to the transposition calculations. This calculates the plane of irradiance for all orientations for every time step. So that's already finished. And then we move into the shading calculations. It calculates the direct beam shading as well as the shading electrical effect. Okay, so at this point, everything's finished and I can step into the scene. And so this is that scene that we were looking at previously, the design that we were looking at previously. And I'll progress the time to, let's say, 8 a.m. And we can see, if we zoom in, we can see some shade shapes, for example, at 8 a.m. And another interesting feature is the ability to toggle on and off some of the terrain-aware backtracking rotation. So I'll toggle that off and I'll move also to 8 a.m. Now this is just for visualization purposes, but at 8 a.m., this is a standard backtracking rotation. Just for visualization, let's look at an area that has some shade. And now I'll toggle on the terrain-aware tracking rotations. And you can see that we've eliminated the shade from most of those trackers. There is still some shade. We can't always eliminate all of the shade. But by toggling on and off, you can get a good visual confirmation that the terrain-aware model is working. Okay, let's take a look at our heat map viewer. This is where we can visualize the 3D results. I can view this in both absolute or relative. So I think relative sometimes can be more beneficial it allows a sort of a more granular sort of look at the results. And we can look at a couple of different shade loss maps. So first is a beam irradiance shade loss, and no surprise, there's quite a bit of shade next to our tree line, shade losses next to our tree line. We can also look at the shade electrical effect losses. Interestingly, that seems, I think because of the shade shape, we get more shade electrical effect losses near this silo. And really around these towers do not seem to have much of an impact. Looking at the transposition loss gain. So even though the terrain-aware backtracking sort of dilutes the significance of the transposition, we can still see that in the kind of generally south-facing slope areas, we have a sort of a boost, whereas in the north-facing slope areas, we have a loss. All right, and then we can look at the overall combined loss gain. All right, I know I'm running through this quick, but let's step out of this and step out of the 3D scene. And now all we need to do to incorporate those 3D calculations into the prediction is just go ahead and run the prediction. So the prediction is running, and we can, as soon as the prediction is over, we can compare that directly to the standard backtracking. And with that, I've actually already curated the results. So I'm gonna stop sharing and go back to my presentation where I'll wrap up. Let me share screen again. And share my screen. And progress the slide. Okay. So this is the side-by-side comparison for the 3D cases that we were just looking at. So standard backtracking on the left, terrain-aware backtracking on the right. Comparing total energy yield, the terrain-aware case has increased energy by about 0.4%. But let's take a deeper look within the loss tree itself. There are 3 primary loss factors to pay attention to. The first is the 3D correction to transposition on POA. This is a new loss factor for version 12 and will be 0% when running predictions without 3D scenes. This represents the loss or gain in the plane of array irradiance for the 3D scene, which will have many orientations, relative to the baseline 2D assumed orientation. In this case, the terrain-aware backtracking case has increased the loss by 1.86% relative to the standard backtracking case. And this makes sense because a terrain-aware backtracking model is choosing less optimal orientations relative to the sun position to try to avoid as much shade as possible. Moving down, we can see near shading has been reduced by 0.89%, which is also expected since the objective of terrain-aware backtracking model is to reduce the direct beam shade. Finally, our shading electrical effect loss has also reduced by 1.39%, which is a result in the reduction of direct shading. The 2 shade loss factor improvements outweigh the increased transposition loss to provide a net boost in energy of 0.42% when compared to the compared to the standard backtracking model. All right, and with that, we'll progress on to our second poll question. So what is the biggest pain point in performing 3D energy modeling? Obtaining accurate topographic data, creating an accurate racking layout in 3D, importing 3D data into performance model, system size limitations in 3D modeling tools, or processing speed. So it looks like the results are coming in. And it looks like the results are pretty, it looks like about a third of people have responded that processing speed is the biggest limitation, and a third of the people have responded that creating an accurate racking layout in 3D is another limitation, and the rest is sort of distributed between the other 3 options. Okay. So with that, I'm going to stop sharing and I'm going to hand over the presentation to Arthur, who is going to take us through more of the detailed side of the modeling and what's happening under the hood from a 3D calculation perspective.
Yeah, I hope everybody can hear me well here.
Yep, we can hear you, Arthur.
Awesome. So thank you, Jason. So yeah, we're going to lift a little bit the hood on what is in this shade engine, transposition engine, terrain-aware backtracking engine. And the first question is how does it really work? The algorithm we have chosen for the shade engine is polygon clipping. When you start looking into how to do these shade calculations, there are 2 big types of approaches that can be taken. The first one is what we would call continuous approaches, that polygon clipping is one of. The second ones are discrete approaches, where you discretize the space. Think about raycasting, ray tracing, pixel counting. This usually comes from the computer graphics community, which is based on pixelized screens. And the real difference here is that on the left, for the polygon clipping, our approach, what you do is you really go along the from vertices to vertices, and you do exact calculations, so that what you render is an exact shape of the shade. It's akin to vectorized graphics if you're used to that. On the other hand, you need to have like little boxes, little grid in to discretize your space. And in practice, what that does is that, let's imagine you have a 1 gigawatt power plant. That's about 250,000 bays if you have 8 modules per bay. For polygon clipping intersecting 2 parallelograms, the number of operations is on the order of product of the number of vertices, so it's going to be about 16. Whereas for a discrete approach, if you want to have a resolution of about 1 square centimeters, you're going to get 10,000 times the number of calculations, 160,000 rays or pixels per bay. So if you go in the truly naive approach for the number of calculations, which is each bay needs to be intersected with every other bay, in the case of polygon clipping, you start with you have 1 trillion calculations, which is already a lot. And in the case of discrete approaches, if you want a resolution of 1 square centimeters, you need 10 quadrillions calculations. That is 10,000 times that. So the reason really why we chose polygon clipping is that it is exact, but on top of that, it is faster. So you have a shape that is infinitely zoomable with no blurry edges, whereas with discrete approaches, you have to do 10,000 more calculations, and you still have blurry edges if you zoom close enough. Now, how is it implemented in practice? What is our workflow? So as Jason described, you upload your PVC or your shade scene, and this is what it looks like in the bottom left here. I'm showing the scene into the 3D, but seen from above. You have these bays that are located in space. The first step is for each time step, we prepare the scene, meaning that we are going to rotate the bays, and each bay can be rotated individually if you have a tracker angle schedule or you have terrain-aware backtracking. And we also rotate our point of view to be from the point of view of the sun. And so what it renders is a 2D scene with the third dimension, the z-axis being the distance towards the sun. And then we do a step that we call broad phase collision, which is for each bay, we determine which other bays it can interact with. So in the top left here, the red bay is only intersected by the one orange bay, but for the other in the lower there, the red bay can be intersected, that red bay can be intersected by 2 other bays. And once we have this list of interacting bays, then we run the narrow phase collision, which is this polygon clipping algorithm. We limit it really to the bays that need to be intersected, and we really render for each bay what is the shape of the shade on it. Our next step is to convert this shade effect to add the electrical effect of this shade for each bay. So the shade shape and the electrical effect of shade are determined per bay. And then what we do is we aggregate that across bays, area weighted for each time step, and we send that to our PlantPredict engine. And this is what you see in the nodal data. And we also aggregate it across time step with a DNI weighting for each bay. And this is just for viewing, it's just what you see in the 3D viewer in the heat maps that Jason showed. So now, in terms of effect of shade models, we have 4 options. I'm going to go through these 4 options. From left to right here, you go from the least amount of effect of shade to the most effect of shade. The first model is the none model, where you do not apply anything. You kind of like have your shade of shape, but you just discard that. You do not apply any reduction to your beam irradiance. You do not add any shaded losses, and this is not very physical, but it's a good way to compare your results. You're like, okay, how much would I have if I didn't have any losses, any shade on this scene? Our second model is the one we recommend for module technologies with a linear response to shade, with little cells like cattail or thin film devices. And what we do is we take the shade scene and we divide the area of the shaded area, the total area for each bay, and so that each bay has a shaded fraction. And this shaded fraction is applied to the beam irradiance, but we do not add other shaded electrical losses to it, meaning that the shade you get is the loss you get. The third model is our new model, our step fractional model. The first step is the same thing. You convert the shade shape to a shade fraction, but then the shade fraction is on top of this shade fraction, we add electrical losses, and this is the model we recommend for module technologies that have bypass diodes or parallel strings, such as crystalline silicon. The last model is our fractional model. It's the historical PlantPredict model. There are some weird inconsistencies with it, so we do not really recommend it at this point. Now, let's dive a little bit more into this new step fractional model. Why should you adopt it? So the idea, as I was saying, is that you convert your shade polygon to equivalent shade fraction, and the electrical effect of shade is determined solely from the shade fraction. So what that means is that you have a trade-off here. You lose the information on the exact shape of shade, but you drastically improve your processing speed. And then this new model, which is developed to replicate the behavior of crystalline silicon modules with bypass diodes, the underlying assumption is that the shade progresses from the bottom of the bay parallel to the bottom edge. And then bay portions are being turned off as we reach a certain shade fraction. So here in the graph in the middle of the slide, on the left, we have a shade fraction that is below 1%. There is no effect, no electrical effect of shade. If you are above between 1% and 50%, you lose one half of the module. If you are above 50%, you lose both halves of the module, and that is equivalent to module with half-cut cells with two parallel strings. So now the question is, how do you determine how many step fractions should you use for your system? Well, it depends on three things: your module technology. Are you mounted in portrait or landscape, and how many high are you mounted? So in the case I was talking about, you have half cell modules, one high portrait orientation. In that case, you use two horizontal step fraction, one for the bottom half of the module, one for the top half of the module. Now, let's say that you change to a solution with modules that have 3 bypass diodes mounted in landscape, too high. In this case, you will have 6 horizontal steps, 3 for the 3 bypass diodes of the bottom module and 3 additional ones for the 3 bypass diodes of the top module. So now that we can do these shade calculations, how can we validate these and how can we compare the results? And in particular against PVCs. So the PVC shade engine runtime becomes fairly long for larger objects. On my laptop, it takes over 1 hour once you go past a couple 10,000 objects. And so the solution that I think most users are used to is to do the fast mode, which is that PVCs run the shade engine for a grid of points on a 10 degrees zenith times 20 degrees azimuth grid. That's all these orange dots for which you do the real calculation. And then everything else is interpolated. So you interpolate your 8760 timestamps, hourly timestamps to get your shade scene. So we don't really have this issue. I think Jason has demonstrated that our shade engine runs fairly fast. We can do more than 30,000 objects in 3 to 10 minutes. So there's little need for this interpolation approach, but we can use that the other way around, meaning that we can calculate all our timestamp, and from there we can interpolate the 10 times 20 points on the grid within the sun path. And this is what we do. And then you can click this export shade factor table, and you get a table that is similar to the PVCs table. The goal of this table, it's not used to run the prediction. It's really for comparison and validation. Because of that, we do not allow the table to be exported all the time, only if you are in a situation that is comparable to PVCs. So that means that you do not have terrain over backtracking on, you don't have wind optimization, wind stow or irradiance optimization on. And so now we can do that. We can run the same shade scene on the left with the PVCs approach, on the right with the PlantPredict's approach, and for the orange dots that are present in both cases, we can do the subtraction. This was on a fairly complex terrain, and we see that for the points that are within the sun path, the two software give very, very close results within 0.3% of one another. So that was a great validation of our approach, with the advantage that in the case of PlantPredict, it goes much faster. So speed, we think, is one of our biggest advantage. And in most cases, we don't think that people will need to do any binning or interpolate or really reduce the number of timestamps they want to measure. But we still offer this option. So the default running mode is detailed. We resolve the shade scene for every single time step. But if you have a lot of scenes to run or really massive scenes that you want to run in a couple of minutes, you have a possible speed up by running a subset of timestamps and then interpolating and extrapolating for the rest of the timestamps. The way we decide which timestamps to model and which ones to interpolate is that we take the hourly analemmas, and for each of the analemmas, we take the minimum, we take the maximum, and we take the point where it intersects the grid. In a balance option, it's every 2 degrees. In the quick options, it's every 10 degrees. So that means that in the balance option, you reduce the number of calculations by about 10. And with the quick option, you reduce your amount of calculations by about 40. But you lose in accuracy at the same time. Another option to speed up your calculations, if you have external object, is that some software that generates PVC files can create objects that are overly detailed. For example, it's hard to see here, but on these little trees, actually each of these little trees is 52 triangles, and that explodes the number of calculations you need to do. So these external objects can be simplified to their bounding box to reduce the number of polygons. Techniques works really well for these trees that they are small, they are compact, and so the bounding box is fairly close to the object. But it can give erroneous results when you have very large concave objects like this wind turbine at the bottom. So what we recommend is, in the presence of external objects, if you have speed requirements, recommend that you analyze the shade object before using the bounding boxes. You can toggle them on and off in the viewer. And if you have any doubts, just go back to no bounding boxes. It may be a bit slower, but it's the safe choice for accuracy. Now, onto the next part. Now that we have reviewed the 3D shade engine, let's see about the terrain aware backtracking and how does this work. So the algorithm is adapted from the work of Kevin Anderson from Sandia National Lab and Adam Jensen from Denmark Technical University. You can find the paper here at the bottom. And we adapted the algorithm for speed and shade avoidance. So we start from the standard backtracking angle for all the trackers. We do a 2D treatment of the neighbor-to-neighbor shade, and if we detect that there's going to be shade on another tracker, it's going to backtrack just enough to avoid shade from its immediate neighbor, assuming that that neighbor does not move. And if shade cannot be avoided, the tracker goes horizontal to maximize the diffuse radiance. That means that it's an individual optimization. There is no combined strategy across the field or global optimization. Performs fairly well on moderately undulating terrain, but it can leave some shade, as Jason showed, when you have higher north-south slope or when you have very long bays, which is the reason why we had this effect when Jason made the demonstration. One thing that is also, I think, very powerful is that you can upload your custom tracker angle directly. You don't have to go to trust our backtracking terrain-aware backtracking algorithm. If you have data from the field from your SCADA system, or if your tracker manufacturer is giving you access to the terrain-aware backtracking angles, you can directly upload a tracking angle schedule, a rotation angle schedule for each tracker in the PlantPredict interface. And these updated tracker angles, they are being passed down to the transposition and to the shade engine, being the ones we calculated or the one you uploaded. All that gets processed in the next steps, transposition and 3D shade engine. And now the last piece of the puzzle is bay level transposition. So now we have bays that can have a north-south tilt. And on top of that, we have each of them can have their own angle, rotation angle. Each tracker can have their own individual tracker angle. So not all modules will be oriented in the same direction. And so we need to do a bay level adjustment of the transposition components that are required. So what we do is we run for each bay, for each time step, we run calculation of each of these components of the irradiance, meaning the direct, the sky diffuse, and the ground diffuse, shown in orange, blue, and green here. To do so, we use the Perez model with the standard inputs, meaning the all-site composites 1990. Then for each bay and for each timestamp and for each of these invariant components, we're going to calculate a transposition factor, which is just a scaling factor from what it would be if it was on a flat surface with a standard rotation angle. And then we average these factors across all the bays, and we pass for each timestamp one scaling factor for direct, one for sky diffuse, one for ground diffuse. In terms of workflow, this is how it looks like. This is the standard case without 3D transposition. You take your baseline irradiance calculation inputs from your infinite shade, you do your transposition model, you get your 3 components of irradiance, and then you pass through these through all your other effects, shading, soiling, IAM, and you get an effective global irradiance. What we do now is that these infinite shade calculation inputs, we take them, we also take the bay level, tilt, and rotation angle, and from there we get what we call the baseline POAI components, and the bay level for each bay, the plane of array irradiance components. From there, for each bay, we calculate a transposition factor for beam, for sky diffuse, for ground diffuse. These, we average them for each time step across the whole power plant, and we correct the beam irradiance, sky diffuse, and ground diffuse irradiance calculated from the infinite shade by these scaling factors for the whole power plant. And you see that in the nodal data. And then we keep going once we intercept the flow, make this correction, and then keep going with your other effects, shading, soiling, IAM. And now we can go with a quick PlantPredict versus PVC 3D feature comparison. So our biggest argument, we think, is system size and speed. So these benchmarks were run on my laptop. And you can see from the charts that with bigger systems, we can go much faster, up to 250,000 times faster, meaning that for 140 megawatt power plant, our software can resolve that in 6 minutes, whereas it takes 28 hours for PVCs, which is why you have to go to the 1020 table and interpolate. I haven't even tried to run a 1 gigawatt power plant in PVCs, but we are able to do that in less than an hour. In terms of features of these 3D enzymes, both of them do 3D beam shading and can do excellent shading object. The shade electrical effect model is a bit different. We use step fractional, PVCs uses partitions, but the advantage is that we can do terrain over backtracking, we can upload custom rotation angles, we can do 3D transpositions. PVCs can do that, but you're limited to the number of orientation that the user defines. For the rear shading, both software perform about the same way. And then when we come to detailed mismatch, we do not have a detailed mismatch. PVC allows that, but only to system up to 5 megawatts, which is not the type of power plant that we are looking into modeling. And with that, we are done with this deep dive into the shade engine, and we're going to our third poll question, which is, what is the largest source of yield uncertainty related to 3D energy modeling? Is it topography of grading data? Is it near object shading from trees, buildings, wind turbines, etc.? Electrical shading losses from shading mismatch? Or is it having access to proprietary terrain-aware backtracking algorithm? I'm going to let people answer for a couple more seconds. Okay, the answers are fairly distributed across the field, with electrical shading losses taking the lead, but not by far. Topography or grading data also there, so kind of like a mixed bag here. On that note, I'm going to move on to the next to our closing notes.
Yeah, thanks Arthur. So I'll close this out. here in the last few minutes. So, so the main takeaway is that 3D modeling is available now and is live now. So version 12 was officially released 2 weeks ago. It is the default prediction logic when you set up predictions now, and it is available for all paid license tiers. I've noticed a couple of questions already in the Q&A related to are 3D features available? What sort of is it additional fees, or is it only accessible in the Pro tier? It is available to all paid license tiers. What's next for PlantPredict? So we're completely overhauling our documentation portal. That's in progress. I'm really excited about that. Our documentation is definitely lagging behind some of the, really the sophistication of PlantPredict. Look for a completely revamped documentation portal by the end of this year. We've also been engaging with several IEs, and we're engaging with them to sort of revamp our validation reports specific to V12. And we hope to be starting to release these in Q1 of 2026. And then also look forward to a new, Rafal, I think we're seeing your screen. Or Arthur. We've got an upcoming webinar on November 19th, PlantPredict and PV Radar. We're going to be doing, we're going to be talking about the some of their updates and their integration with PlantPredict. And with that, we'll take it to the Q&A, and I think we've run a few minutes long. But before we get into the Q&A, I just want to say thank you for joining, and also for everybody who submitted Q&A questions. We'll respond to those directly after the webinar, typically within a couple of days. And so with that, I will take first Q&A question. So you make a convincing case that polygon clipping is a good approach to model direct beam shading, but what about, are there any disadvantages, or are there any advantages to discrete approaches, such as for diffuse shade or back of the module sort of irradiance modeling? Arthur, do you want to take that?
Yeah, sure. Yeah, the first slide in the technical part was not to say that discrete approaches are inherently bad, or that one approach is better than the other. And yeah, I fully agree that for like back irradiance of the module, or for diffuse shading, techniques like ray tracing can be very powerful. Ray tracing in particular, if you have multiple reflections, can really help you. So yeah, we think our thinking is that both approaches are valid. When it comes to frontside beam irradiance shading, polygon clipping will always be faster and more accurate, or doesn't have to induce a resolution issue.
Alrighty, next question. Can we do fixed tilt designs in Terabase? Yes, you can. Fixed tilt designs are fully supported. And maybe one more question. Is the 3D shading API access well documented? I can see that being powerful, but also hard to interact with programmatically. So yeah, one point of clarification. So all of the 3D features are API accessible. Our map interface and really the GIS workflow is the one part, we call that map builder, that is not API accessible. But we are working to update our API documentation along with our larger documentation updates. So we hope that that will be published very soon, within the next couple of weeks. So, and with that, I think that brings us to time. Apologies. The recording will be made available to all attendees, and thanks so much for joining.